Thanks, Sasha. So I'm very happy to be here. Thanks to everyone for sticking around until the very end of the workshop. I'm sorry I couldn't be around for the first 2 days. I don't even have the excuse that I was teaching, so really no excuse. Sorry. OK, so today it's going to be a slightly more philosophical talk than what I'm typically comfortable with, but let's see how it goes. So in particular, there will be no new mathematics. It will be only very classical mathematics, but hopefully it can be used to tell us something slightly new about a new problem, which are these adversarial examples. This is joint work with Eric Price and Ilya Rasenstein. Ilya is a colleague at Microsoft Research, and Eric was visiting us for a couple of months, and that's when we did this work. Otherwise, he's at UT Austin. OK, so let's talk about robust machine learning. So I think I'm the first talk in the workshop to talk about this, which is surprising because I believe it's a pretty important topic. But let's see what this is about. OK, so what do we want to do? So we're going to only be concerned with binary classification. OK, it's just the most simple thing. We have two classes, and we want to distinguish elements from those two classes. So what does it mean exactly? We have two unknown distributions, mu and nu. OK. And you receive samples from them. And what you want to do is you want to find a set A. And you want to say that elements that fall in this set A, I'm going to classify them as coming from mu. And elements outside of A, I'm going to classify them as coming from nu. OK, so the errors that I make are mu of the complement of A and nu of A. OK, these are the two types of error. And I want both of those errors to be small, less than 1%, some fixed number. OK, so this is what binary classification is about. It's finding this set. Now, what is robust classification about? So if you want to be robust with respect to a certain set of perturbations k, you want the following. You want not only that, say, under mu, you have a small probability to fall in the complement of A, but you want also to have a small probability to fall close to the complement of A. So the complement of A is where you're making mistake, and now you enlarge it by adding this set of perturbation k. Okay, so you want not only mu of A complement to be small, but mu of A complement plus k. Okay? And you want this both for mu and for nu. Okay, so this is robust classification. And in this talk, we're only going to consider the following type of perturbation. So everything is going to be in RD. Okay, so we're going to have d-dimensional examples. And the type of perturbations that we will consider are perturbation bounded in L2 norm by epsilon. Everything that I will say actually applies to any norm. Okay, so it's not specific to L2, it's just simpler in L2, but any examples that I will construct, you can rotate it, and L infinity and L2 are the same on the rotated sets. Okay, but just say again?
You need to know what k actually is, or?
So we're not really going to talk about algorithms, so it's not going to matter. But yeah, let's say you know what k is. I mean, typically that's what you want. You know what kind of perturbation you want to be robust against. Okay? So I'm absolutely not trying to going to try to justify why this is an interesting problem. If you want, go on YouTube. Go find a lecture by Alexander Madry, and you will get enough motivation for this. Basically, just think, imagine a self-driving car. You do want it to be robust, right? I mean, you don't want it to be sensitive to, say, I put a little post-it on a stop sign, and then suddenly it thinks there is a road over there. Okay, so you want to be robust. It's definitely very important. Okay, any question on the setting? No? Setting is clear? All right, so so today I'm putting my machine learner hat. So I'm going to be a good machine learner, and I'm only going to tell you about the history of the problem in the machine learning community. Okay, it has, of course, a very long history in many, many other fields. There is robust statistics. There is robust optimization. I'm ignoring all of this. Okay, very good. So this was initiated in the study of robust ML was initiated in a very influential paper by Dalvi, Domingos, Shanghai, and Verma in 2004. And the original motivation makes a lot of sense, which is spam filters. Imagine I have designed a spam filter, then the spammers, they are going to try to overfit it and try to adversarially perturb their spam so that I actually do not detect them. Okay, so it makes a lot of sense that in this context you want to be robust. And at the time, SVM was the big deal. Everybody was using that, so linear learning. And a couple of years later, Globerson and Rorice, they showed that, in fact, robust classification in the linear setting, it is tractable. It's just another convex optimization problem. So you can actually learn the most robust linear classification algorithm. Okay, so very good. Now, fast forward to today, or actually 5 years ago, this paper, which has now thousands of citations, Szegedi et al., they pointed out that neural networks are actually very, very brittle. Okay, a tiny bit of perturbation, and you can make them say anything you want. Okay, so this was, I think, a surprise in 2013. By now, it's a very well accepted fact that just if you train a neural network without thinking about robustness, it's not going to be robust at all. And it's very easy theoretically to see why, and we're going to see a couple of examples later on. But the important point is that there is an entire community trying to fix this issue. Okay? In fact, I would say thousands, if not tens of thousands of people on the planet trying to do this. And as of today, as of January 2019, we have very moderate success, I would say, on having robust models. Okay? So on MNIST, we're doing kind of okay. So MNIST is one of those very simple machine learning data set. We can get 96% robust accuracy, and moreover, it's provable. So I'm not going to emphasize this too much, but this is really a very interesting avenue of research that emerged in the last year or so about not only being robust, but being provably robust. If you go to CIFAR or ImageNet, as of today, the results are really shitty or really bad, but sorry. But who knows? I mean, I don't know about all the ICML submissions. There are thousands of them. Maybe somebody is doing something good.
So the state of the art is for infinity norm, and this is the certifiable types of things?
Yes. So provable means certifiable. And when I say moderate, I mean it's with respect to tiny perturbations. Yeah. So it is in L infinity. Yeah, like 0.001 something. Something tiny. Something ridiculous. That you want to be robust to something much higher than that. And the question, I look at this, and the question is why? Why is it that we're stuck like this? What's the reason? Okay? So I'm going to put forth 4 possible explanations for this current status quo, and we're going to discuss all 4 of them. Okay? So that's the plan for the lecture. Okay, so in our paper, this is from May 2018, so the month is important in this, in this field. So these are the hypotheses. Yeah, I don't know the date. Yeah, actually, month is enough. You don't need the date yet. But yeah. Okay, so first hypothesis, just there exists no robust classifier in the task that we care about. Say for vision, maybe it's just impossible to be robust to these adversarial perturbations. That's definitely one possibility. Another one is that there exists a robust classifier, but you cannot find it with a small number of samples, with polynomial number of samples. Okay, maybe you need, information theoretically, you need really many, many samples because you have to compete against these exponentially many adversarial perturbations. Maybe. Third hypothesis is, neither one is true nor 2 is true. So there is a robust classifier. You can find it information theoretically with a few samples, but you cannot find it computationally. Okay, that's hypothesis 3. And hypothesis 4 is just we don't have the right algorithm yet. Okay, so this is also definitely a very real possibility. Okay. Yes, please. Excellent question. We're going to address this question. Okay. Yes, this is an excellent question. Okay, I don't want to answer it now. Okay, so these are the 4 hypotheses. Okay, and there are papers on each one of them. So let's discuss them because it's pretty insightful. So first one, no robust classifier exists. So let's see one paper in favor of this. So this is the fuzzy, and fuzzy observation. This paper is, so these are brothers, 3 brothers. Adversarial vulnerability for any classifier from February 2018. And it's very closely related to this paper, which got some attention, at least on Twitter, adversarial spheres by a team at Google Brain from a month before, okay? January 2018. So let me just think how I want to do that. So I'm going to tell you like this, and then I will draw on the board. So here is the example. So again, the title says it, okay? Adversarial vulnerability for any classifier. So what they want to say is that it doesn't matter what your classifier is, it will always be susceptible to adversarial attacks. Okay, so it's in this no robust classifier exists. So let's consider a Lipschitz generative model. What do I mean? I mean that you take the latent variable z is some Gaussian. Okay, so you have a Gaussian variable, and then you generate your images or your input x from applying some Lipschitz map g. Okay, so this is just a very general Lipschitz generative model. And then let's assume that we are in a very simple case where everything is balanced. Okay, so the 0 class and the 1 class are roughly of the same size. Then what happens is the following fact, which is, I guess, surprising the first time you see it. 90% of the samples in such a setting will be susceptible to adversarial perturbation of size of order 1, while the samples are of size of order square root d. So of course, for people who know about Gaussian concentration, it's not at all surprising, but still. So let me just draw a picture. Is there a question? No? So the picture is like this. Right, so this is my set A. And let's say A has probability roughly a half. Okay, the probability of A is roughly like a half. Okay, it's some constant. Then, and let's say this is in the latent space. Okay, in the latent space we have the Gaussian measure. Then the Gaussian isoperimetry tells us exactly that if you extend this by some constant O of 1, you have this new set. Then if this was a half, then this new set is in fact 90% of the samples. And you can apply the same reasoning to the complement. Okay, so you have the complement, and now the complement is of size roughly a half, and everything at distance, some constant from it, is 90% or 95, whatever. So you know that, in fact, everything has to lie in here. Okay, so in the Gaussian space, everything is at distance, some constant from the boundary of your classification. Now, what do? We apply this Lipschitz map. So if it's Lipschitz, it distorts the distances only by a constant. So if for every point here, I can move by a constant to get in A, then it's also true in the image through the Lipschitz map. Okay, so this is just a mathematical fact, and on the face of it, it seems pretty damning. But what's the catch, to me at least? The catch is saying G is Lipschitz. This is very, very strong. This is saying that you're doing a very small perturbation of the Gaussian measure. And I think nobody believes that you can generate natural images by applying a Lipschitz map to a Gaussian random variable. Okay? We're going to talk more about those generative models. You can think, for instance, G is a neural network. Then the Lipschitz constant of this neural network is basically related to the product of the spectral norm of those things. So of the matrices that are doing the linear operations before the non-linearities. So you can imagine, say, if the weights are all constant, this can be of order of the number of parameters. So it's very, very big. Okay, so this is the catch. This makes basically this argument invalid, in my opinion. Okay. Now, what's an argument against? Well, humans. Right? I mean, we believe that we are pretty robust. It's hard to think that, you could change a few pixels here in this picture and suddenly I think I'm on the beach in Hawaii. I think it would be nice, but that being said, I should also say definitely there is no consensus. So this is one paper, again, from the same time, basically same group, adversarial examples that fool both computer visions and time-limited humans. Okay, again, the title says it all, but also, people sometimes bring up like optical illusions as an example of adversarial examples. That's not at all what we're talking about in this talk, right? Because what we want is for the bulk of the images, right? I allow you some 1% error. So the optical illusion, you can definitely put it in the 1% error that humans do on typical natural image. Okay, good. Yeah, and what I want to say also is that the fact that humans are somewhat against the proof that robust classifier exists, it's really not clear because it's hard to imagine the exponential power, of trying all the possible perturbations. maybe there is a perturbation that would make me think that I'm somewhere else. It's hard to test. So I would be quite interested if there was a way to set up a neuroscience experiment to test this. I don't think it's impossible, but I don't know how to do it. OK, so this is it. So again, just for every hypothesis, it will be like this. There is no clear consensus. We don't know what is the right answer. OK, I'm not going to tell you the answer. I don't know. OK, hypothesis 2. Identifying a robust classifier requires too much training data. OK, so again, let's do the same exercise. Let's go through arguments in favor and against. So in favor of this is a very nice paper by Schmidt, Santurkar, Tsipras, Talvar, and Madri. Adversarially robust generalization requires more data. OK. April 2018. OK, very good. So let's see what is the example. So the example is pretty nice. So let's consider the following task. So we have two distributions. These are two Gaussian distributions, OK? And one is centered at theta, and the other one is centered at minus theta. And theta, let's say, let's see, what do I want? Theta is also a random Gaussian. OK, so the picture is like this. This is a sphere of like square root d. OK, I'm taking a random theta and minus theta. And then my two other distributions are two centered Gaussian. OK, so this is n theta sigma squared times the identity. And this is n minus theta sigma squared times the identity. OK? And now I'm going to get samples from those two distributions. I get a new sample. I want to classify it. OK? Very good. So first, let's just think for a minute what kind of sigma we can allow to have something non-trivial. So maybe it's not totally obvious, but you can actually, even with sigma squared of order d, you can distinguish. OK, so this is not totally obvious because the separation is of order square root d. So if I have a sigma squared times the identity, then the separation, and sigma squared is like d, then I have a huge separation of order d. I mean, a huge overlap. Right? So the sphere, they look like what I'm telling you right now, is the situation is like the distance between the center is square root d, but the balls are huge. Okay, they are basically of size d. Okay, and I have another ball here. Okay, and I'm telling you these two balls, you get random samples, you can tell which one it falls from. Okay, so first time you see this, it's not obvious what's happening, and how am I doing on time? Yeah, so just as a simple calculation to see it, if you have never seen it, just look at the relative entropy. So you can look at the total variation distance between mu and nu, and just apply Pinsker. This is smaller than square root of the relative entropy between mu and nu. And in fact, for Gaussian, this is morally tight. Now, for the relative entropy between two multivariate Gaussian, apply just the chain rule. So you have d components. For each component, you're going to get the total variation distance between those two things. So what you get is smaller than the sum. And then the distance on the i's coordinate is like theta I squared over sigma squared. Right? This is just the relative entropy between a Gaussian centered at 0 and a Gaussian centered at mu at theta I with variance sigma. So what you get is this is equal to square root d over sigma squared. So you see, for this to go to 0, for those things to be indistinguishable, you need sigma squared to be like d. Okay, just this is just an aside. It's cleaner than many of the proofs that I know. OK, very good. So we know that you can take sigma squared as big as d. Now, what? Question?
Show that you can
Yeah, but for Gaussian, it's like tight, this first inequality. But indeed. Yeah. So I have mu and nu. Okay, these are my two distributions. And let's say I take sigma squared to be like d. Okay, sigma squared is huge. Then the typical distance from the center is going to be like d. So it's huge balls, but in fact, the picture, you know, this is not the correct picture. The correct picture is like, you know, this is one sphere, and this is another one. So basically, they just overlap in one of the tentacles. That's what's happening. Okay. Okay. Very good. All right. So, okay. So what do I want to say? All right. So let's analyze now the complexity of this. So I'm gonna not do the calculation too carefully, or we could do it. It's very simple. So there is only one reasonable classifier for this thing. You get those samples. You're just gonna try to estimate what is theta. So how do you estimate that? You take the empirical average that you got from that, from mu, minus the empirical average that you got from that one. Okay, and now you just do a linear classifier with respect to this. So this linear classifier here is going to be W. There will be theta plus sigma over square root n times z, where z is also a Gaussian. Okay, this is what you get when you average the samples from those two things. Now, what is the error, the classical error that you make? Well, take a new sample, say from the first distribution mu. So a sample is of the form theta plus sigma z prime, where z prime is a Gaussian. And what you want to know is it true that with high probability, the inner product with my W is non-negative? If that's the case, then I classify correctly. So a very, very simple calculation, you just look at the order of magnitude of all of the terms, tells you that d should be much bigger than sigma square root d plus sigma squared square root d over n. So you see, when n is infinite, then you recover what I told you, that sigma squared should be like d. Right? So you recover this relative entropy analysis through this calculation. But more interestingly, when n is equal to 1, when you have a single sample, then in fact, as long as sigma squared is smaller than square root d, then you can distinguish. Okay, so what I'm saying now is this is a problem where with n equals 1, a single sample, and if sigma squared is smaller than square root d, you can get non-robust learning. Okay, and your learner is just, you got one sample that gives you an estimate of theta, and then when you get a new sample, you say, is it closer to that sample or to minus that sample? And when sigma squared is smaller than square root d, this is going to be correct. Now, the important thing is the following. Adversarially, say in L infinity, the situation is much worse. Because adversarially, what could the adversary do? When you get a new sample from mu, theta plus sigma z prime, I can push it in the direction of the noise that you get on your sample. So the noise that you got on your sample is this z, which is roughly bounded in L infinity norm, up to some logs. I can just push in the negative direction of z. Okay, so now your example, it was theta plus sigma z prime, but now I add the perturbation minus z. So if you want, it's like I have those two distributions. I got some average here and here. Now I get a new point from this distribution, and I'm just going to push it towards that point. That's my adversarial perturbation. But you can see in this picture, if the balls are crazy overlapping like this, then of course a small perturbation is going to put me in the other one. Okay? So that's what happens. Basically, when you just do this calculation, you will find that this is negative, meaning that you do get an error with high probability if d is smaller than sigma d over square root n. You see the difference is this sigma squared square root d became sigma d. Okay? And you just simplify the d, and you get n is smaller than sigma squared. So what this is saying is that impossible to robust learn if n is smaller than sigma squared. So take, for instance, sigma squared equals square root d. At sigma squared equals square root d, a single sample allows me to learn non-robustly. But if I want to learn robustly, I need to see square root d samples. Okay, so this is a very easy example, but it shows a polynomial separation. It shows that in some cases, you do need more data to be robust.
Like here, the size of your perturbation in L2 is like orders per.
Yeah.
I mean, what is the right order? Like you write it in L infinity, okay, so it's 1. If I do whatever I want, then I can make all those numbers.
Yeah. Sure. So, okay, this is another talk. What is the appropriate norm to consider? I think L infinity is actually pretty natural to consider. As I said, the other results that I will talk about, they do generalize to L2. It's true, this example, I'm not sure how to do it in L2. But, okay, maybe actually I do. You can just, you replace the Gaussian by just on a cube, and then you rotate the cube so that L infinity and L2 are the same thing. And that should do it. I think, but okay, I didn't check. Yeah, I think this will work. Okay, so this shows, notice, this shows only a polynomial separation. Okay, so it's an argument in favor of the fact that you need more training data, but it doesn't say you need exponentially more. You need a little bit more, okay? So against is what we wrote in our paper. It's very simple, but somehow it felt like we had to write it, but it's really, really simple. So imagine you know that the world is only consists of capital N distributions. Okay, capital N could be exponential. Or in fact, you don't even need to know a finite, you just need to know a covering number for your set of distributions. So say that you have many, many possible distributions, but they can be covered by what we call Wasserstein balls. Okay, Wasserstein balls, it doesn't really matter what it is, but it's what you imagine if you know what is the Wasserstein distance. Then the point is, once you know this, then just log n samples suffice to find information theoretically a robust classifier, if it exists. So just to make this slightly more concrete, let's go back to the fuzzy and fuzzy generative model. So imagine that you have a neural network, which is given by n parameters, capital N parameters, and all the parameters are between -1 and 1. This is pretty natural, actually. Then this n, sorry, what's happening? This n is basically going to tell you that, sorry, it's not the same capital N, actually. So if you have capital N parameters, then what our theorem implies is that with only capital N samples, you will find a robust classifier, okay, information theoretically. So for instance, you can apply it to this setting, and in this setting, it will immediately tell you that if you have D samples, then you would find the robust classifier. Okay, so in general, I think...
So this is an information theoretic statement.
Yeah. And a trivial one, I would say. But the moral of the story is basically, if you have any reasonable setting where you believe your distribution can be described by D parameters, then roughly D samples will tell you what is the most robust things that you can do. There is just no magic. I mean, no difficult magic. Okay, so I think the jury is still out. It could be that we need a little bit more samples than what we have currently, and maybe 2-3 years down the road, we just have enough samples, and then we have robust models. This is possible. This is not ruled out by anything that I'm telling you today. It's a world we could live in. Okay, now hypothesis 3 is my favorite one, and it's the one we push in the paper, which is that you can do it information theoretically with few samples, but you cannot do it computationally. Okay, so here is the main meat, but again, it's just going to be a simple, stupid example like those ones. So here is the theorem. So there exists a binary classification problem such that all examples are in a ball of size square root D, just like all the things that we have been talking about. You can learn non-robustly super easily, say with a linear classifier and with polysample, you can do everything very easily. This binary classification problem, it admits a very robust classifier. So things are in a ball of size square root D, and you can actually perturb things by 0.1 times square root D. So you can really do like macroscopic movement. Okay, you can do huge movement. this guy can be found sample efficiently, and to answer your question, it is efficiently computable. Okay, so it's really a robust classifier that can be implemented by a small neural network, and it's a nice guy. Yet, finding even an epsilon robust classifier is computationally intractable. I will say, what do I mean exactly? Even if you restrict to adversaries which are themselves computationally restricted. Okay, so I don't even need to have access to super crazy adversaries. Like a very simple adversary will suffice to mess up any robust classifier, any efficient robust classifier. Okay, and the notion of intractable in this theorem is kind of the strongest is that we have right now. Namely, that you would break RSA if you did, if you find something that works for these settings, then you break RSA, okay? Or you can factor large integers. Okay, does the statement make sense? Okay, so this is really saying that restricting the adversary, assuming that there exists something very robust, this is still not enough to make the problem feasible in any meaningful sense. Okay.
Sorry, I'm confused about
please.
The relation between 3 and 4. So
yeah.
The end of 3 says like n computed efficient?
Yeah, very good. You see, this robust classifier, it could be a crazy algorithm.
Okay.
What I'm saying in 3 is that this robust classifier is not a crazy algorithm. It's just that you can't find this non-crazy algorithm. So like 4 is about the learning process, 3 is about the end result. Yeah, makes sense. But thanks for the question. That's very helpful. Any other question on the statement?
As in the perturbations can be computed efficiently. That's what the end of 3 is saying? Or,
no, that's the end of 4. That's the end of 4. The end of 4 is saying that the perturbation can be.
Okay.
Yeah, so let me say one more time 3. So I'm assuming that there exists a mapping from RD to 0, 1. Right, which tells me for each example whether it's class 0 or class 1. And this mapping is a polynomial time mapping. That's what I'm saying in 3. Yeah?
So once you actually know all the variables, that it can be run fast.
Yeah, if you did know the robust classifier, you could run it fast.
But finding those variables is...
Yes, exactly. Yes, exactly. Yeah, let's leave that to the discussion section at the end. But yes. Yeah.
Are you going to describe the...
Yeah, of course. Yeah. So, that's basically what I'm going to do for the rest of the time. So, what's the basic computational abstraction? Basic computational abstraction is trivial, and anyone in TCS will say, okay, of course, and it's true, of course. So, consider those 2 examples. So, the distribution mu is a point mass at 0. Okay, so the first coordinate tells you the answer. Okay, and then the rest is just uniform on the cube, just uniform minus 1 to the d. Now the alternative, again, the first coordinate tells you the answer. It's epsilon times the point mass at 1. Okay, so just you look at the first coordinate. If it's 0, it's a class 0. If it's epsilon, it's a class 1. But then you product it with a pseudo-random generator. Okay, so a pseudo-random generator is exactly something that looks like a sample from the uniform distribution, but it's not. Information theoretically, it's very different, but computationally, you cannot distinguish it. Okay? Say again?
The first coordinate is delta epsilon.
It's delta at epsilon, that's what I meant. Sorry. Yeah, thanks. Yeah, this is a terrible notation. It's just wrong. I meant delta at epsilon. Yeah, thanks. Thanks, Andrea. Okay, so by definition of a pseudo-random generator, if you remove the first coordinate, which you can definitely do even with an epsilon adversary, if you just, collapse the first coordinate, then you're left with distinguishing uniform distribution from a pseudo-random generator, which you cannot do efficiently. Now, I still need to argue that there exists a robust classifier for this problem, but that's a very simple volume argument. The point is that a pseudo-random generator, you can think that because it has to be efficient, it's supported on a polynomial, like a small size, a small subset of the cube. Okay, so in terms of volume, it occupies a very tiny fraction of the entire cube. So when I take a sample from the second distribution, even if I modify it microscopically, I still don't get a typical sample from the other one. Okay?
Sorry, can you remind me what the scene length for such a PRG should be?
Well, yeah, I will explain that on the next slide. Right now, you need blow up 2. Just you know, if you have a seed length n over 2, you can blow it up to 2, and that will apply here. Yeah, just any constant blow up will give you the exponential gap. What? Yeah?
This classifier can be computed, this robust classifier can be
Yeah, of course. Yes. So this is the basic computational abstraction. So this is not enough to prove the theorem. So this doesn't quite yield our theorem. Oh yeah, by the way, I forgot to say, so there are 2 papers on the archive, May and November, and in November we added Yin Tat Lee, my good friend and excellent collaborator, and we worked on this during the summer. Okay, so this doesn't quite yield our robust classifier because exactly our robust theorem, because this robust classifier is not efficiently computable. In fact, by definition, I mean, it's kind of the definition of the PRG. So the fix is to consider what's called a trapdoored PRG. So trapdoor just means that there will be like a secret key, and if you know the secret key, then you can tell between the two. Okay, so information, theoretically, we will be able to search over the key, but computationally, we can't do that. So maybe I will go fast on this, just to give you some feeling for what this looks like. So this is the famous Blum-Blum-Shub pseudo-random generator from '86. So you take just the product of 2 large primes, okay, P and Q, which are both congruent to 3 mod 4s. That's important to have quadratic residue. You take a random quadratic residue. Okay, so you just take a random integer between 1 and n, which has a square root, mod n. And then you just apply the square root iteratively. The point of taking them congruent to 3 mod 4 is so that you can take the square root as long as you want. So you keep taking the square root, and the transcript that you output is just the parity of the square root. This looks pretty random to me. I mean, what is this? So the theorem is that BBS allows for a polynomial blow-up. So that just means that from a random seed of size d, you can get something that looks random up to size d to the c for some constant c, under the assumption that integer factorization is hard. Okay, so this is the key thing. And now the key new ingredient is that this process, so the distribution now I'm going to give you the seed and the output. And the point is that even if you know the seed, you still can't tell if the transcript came from that seed, because we don't know how to take square root efficiently. Okay? The only way to take square root efficiently is to know the integer factorization, the prime factorization of n. Okay, so again, the new distributions are, I'm giving you the seed, and I'm giving you either a uniformly random transcript, or the transcript which is obtained by taking iterative square roots and the parity of the square roots. And the point is that even knowing the seed, you cannot tell, but if you knew the factorization, you could tell. So information, theoretically, you can apply the statement that I told you before. You will find with just D samples, you can find it, but in polynomial time, you cannot do anything. Okay? And again, the robust classifier here is efficient, because taking square root when you know the key is efficient. Okay? So that's the big difference with the previous statement. Okay. So I realized that people in machine learning don't like pseudo-random generators. So here is a slightly different construction, which probably people still won't like, but at least it's closer to think that we could care about. So imagine, so this is a different construction that yields a weaker result, but does not rest on cryptographic assumptions, hardness assumption, but instead rests on statistical query lower bounds. So I won't explain in details, but I will just tell you what is the construction, because it's somewhat insightful. So imagine your null hypothesis, I mean your class 0, is just a Gaussian, random Gaussian. And the alternative is random Gaussian except on a k-dimensional subspace, So in a k-dimensional subspace, instead of being Gaussian, it's a discretized Gaussian. Okay, with some small error 1 over square root m, where you make the discretization such that the moments, they match up to order m. The point is, you cannot find this k-dimensional subspace except by scanning over all possible subspaces. Okay? Unless you compute moments of order k, but this will take you time d to the m. Okay, so if you work out all the details, I will skip this. You set all the parameters appropriately, and now what you get is, even assuming a square root log d robustness, before we were assuming square root d robustness, so this is much weaker, but it's still a big robustness. Even assuming square root log d robustness, you cannot learn efficiently a robust classifier in this problem if you have less than an exponential number of queries to an exponential precision statistical query oracle. Okay, I won't say more than that. Okay, is there just a quick question on this before I move to the conclusion?
So just to
Yeah.
be clear on the PRG problem that you described, it's a testing problem. It's not really, I mean, we can probably, since it's
Yeah.
probably enough to put that low bound for a testing problem.
Sure, yeah.
We don't really use the fact that testing and classification are
No, wait, no. You can think about it as a testing problem. Yeah. Okay, so here is the conclusion. So I told you about 4 possible hypotheses, and now I will tell you what I personally think, and as an output of this research, not just prior on the problem. So no robust classifier exists. I think that's probably not true. But this is maybe where I have the weakest evidence. Yeah, I'm not sure what else I can say. I mean, if it's true, then okay, there's nothing we can do. So let's assume it's not true. Now, second one is identifying a robust classifier requires too much training data. So I put maybe, because as we saw, there could be a small polynomial gap between robust and non-robust. And we know we can learn those problems non-robustly. So maybe, a couple of years from now, we have 10 or 100 times more data, and then suddenly everything works out. I doubt it, but who knows? So jury is still out on 2. The third is this computational intractability. This is definitely true in general. I mean, we saw, like, in general, yes. Even if information theoretically you can do it, and there is a very robust one, still in general you cannot do anything, even if the adversary is computationally restricted. But here is the key point. It's definitely true in general, but maybe not for the tasks that we care about. So the examples that I gave you, they really have the flavor of distinguishing 2 different types of noise. But what machine learning is about is exactly not distinguishing that type of noise from that type of noise. It's about distinguishing structured data, right? So what kind of further assumption can you make about the distributions themselves? So to answer one of the previous questions, I think that's one of the things that I'm most excited about, which is not actually assuming something about the classifier, but more assuming something about the data itself being structured in some way. I don't know what is the right hypothesis. And then number 4, we just have not found the right algorithm yet. I think this is the right answer, but we need models. So 3 and 4 are tied together. Right? What this research tells us is that you need to make more assumptions about the distributions that we're facing, and then once you have the right assumption, maybe you can develop better algorithms. Okay, that's all I have. Thanks.
I don't know what the list of the that are solving this problem is. Presumably, you had a paper in April, and somebody told you, but you cannot compute this efficiently, and then you had a paper in December. But what is the...
that person being hint at, but...
Okay, but what is wrong with not being... Because you could also add as to your list the fact that you can also sample efficiently from most of the distributions that you have, right? But then why is this one important, the one that you can compute?
So yes, what you just said is reasonable, but notice that the example that I told you about the PRG, I mean, it does satisfy this. You can sample. You can take,
that's what I'm saying.
yeah.
But then, so what's wrong with getting, if the robust classifier that was robust, that you exhibited, the fact that it's not efficiently computable, is that leading to some sort of logical fallacy like this thing?
Yes, you don't want that, but even that we can also remove. We can assume that there exists one which is efficiently computable. So yeah, I mean, it seems like, and people keep saying, okay, but what about if you add this? But then I can also find, like basically everything that people have asked me, I can find a counterexample. So that's the problem is I don't know what is a good assumption to make so that there are no counterexamples like this. I just don't know. There should be one, but I mean, hopefully there is one. Yeah?
So typically when we do these adversarial things, we put a norm, like the input space that measures how robust we are. But if I think of, like, say, images, right, it doesn't seem to me that the dimension of the input space has, I mean, I can take a 1 megapixel image, 20 megapixel image, 100 megapixel image, and somehow the norms, like the MIFODS norm would start direction more and more, but somehow that doesn't seem to matter to the actual form of recognizing an image, right? So somewhere is that intrinsic dimension in which we can trace adversarial forms, or?
Yeah, that's an excellent question. It's just an excellent question. Yeah. Whether, yeah.
So there's something between 2 and 3 as well, right? Where
There's something what?
something between 2 and 3, where you need more samples if you want to be computationally efficient. But then
Yes.
there exist
Yes, that's true. Yes.
versus computation trade-offs exist.
Yeah. No, absolutely. Yes, that's true. But here, notice that again, I'm working, when I'm looking at 2 or 3, I'm working on the assumption that there exists something very robust. It's there, it's super robust. And the question is, can you find something which is at least, maybe a tenth of that robustness or something like that? So you're making a strong assumption to begin with. So these statistical computational trade-off counterexamples, I don't know if they work in this regime where you assume something very separated. That's basically the difference. Yeah.
Between assumptions on the original data and other non-computational restrictions on the adversary.
Yes.
The model-based assumptions on the data is more.
Okay, I don't want to make that statement. Yeah. All of these are, I think, interesting avenue of research.
Okay, let's thank Sebastien.
Thanks.